Okay, so this is homework one is coming back. Homework one solutions are posted online. So if there's little points off at places, there's a little more discussion online about that. So I encourage you to look at those. You can bring in anytime and ask about those different parts or other aspects of the book as you're interested in them. Generally, the scores were quite good. 16s and above, 14s and above. So getting most of the points. This one had a little more discussion. There's a little bit less in the book about it. So mostly people are on track with things. And so if you do all the homework and get most of the points, you'll be in a good position to be ready for the exams and the final, and all set to do a project. So stay with it. As you've seen, the second homework and the other one, a lot of it becomes more numerical because we're using data and things, and so parts of it are more direct answer. Some of it's still interpretation. So let me know if you have any questions about it. So today we're going to talk about conditional probability. Last time we talked about introduced probability. Homework 3 is posted. That's due next Wednesday. That concerns some of this stuff with probability chapter, and we'll do more on Monday. Okay. So on the handout, conditional probability, right, is a probability that one event happens given that another one does. So if A and B are two events, right, probability, it gets written as A with a vertical slash B, means that probability of A is true given that B is true. Yes?
Can you figure this out?
Oh, you figured it out?
Or should I do that?
You can do it after class. I'll be around for a little while after class. So
Thank you.
that's fine. Sure. It might be expressed slightly differently in different language. A has occurred, or we're looking at a group A. What's the chance? What's the probability? B has occurred in this symbol. The thing on the right is kind of like a denominator. It's written as a vertical line and not like a fraction, but you can think of it kind of like a denominator. It's the set that you're focusing on, not the whole, but just B. Maybe it's given that B has happened, or if B is true, what's the probability of A? Now, a way of computing it is the probability of A and B divided by the probability of B. So our formula that we'll have for conditional probability is if A given B is going to be the probability that they're both occurring over the probability of B. And so this is the probability of A and B that they're both occurring over the chance that B does. And so the thing to the right becomes kind of like a denominator. So you keep it down there. So questions like this is, given if B is describing the current weather out there and what you're seeing, what's the chance that it's going to, snow on a day like this? Or given that somebody studied, 10 hours for a test, what's the chance that they're going to get a passing grade? So given information, what is the chance that that A is going to happen? And sometimes you could reverse it. Sometimes you have information about the other way things go, and however you define B and A, you might write it like this. This would be A in the denominator. Now, following exactly that pattern, we'd write B intersection A over probability of A. Right? But A intersection B, B intersection A is the same thing. Right? It just means that they both happen. So you can reverse this like multiplication. It's commutative. You can flip it. The thing to the right that you're conditioning on, or you're given, that subgroup you're looking at that qualifies as A goes in the denominator in there. Right? So you can say the probability that both A and B happen over this probability of B, probability A, sorry. And so we will apply this to a whole range of different circumstances, right? Where we know some information about A, maybe something information about B, and then we know there's the joint probability of two things. One consequence of these two equations is both of these we could write for probability of A intersection B in terms of other things. That is, we could rearrange these to solve for A intersection B. If we do that, the chance that two things happen can be written as a probability of one of them, and then a conditional probability. Right? So you could write it as the probability that A happens, the first event, times the probability the second event happens, given that the first has already happened. B given A. So if you know A, like disease status of individuals, and these are testing status, right, you could ask questions like that. Alternatively, if you use the other equation, you know, A and B might just be, they're just letters in the alphabet. They might be arbitrary in terms of their order or what you would know. You might know this one, and depending on how the problem is phrased and how we use these letters, right, you might have this other one. So again, this would be, and then times the probability that you know this one, that conditional probability. Now we give you the probability of both of these things, right? And anything else, right? So yeah, there's a few notes there. And let's use this in an example. So let's say that you have 3 seed companies. And they're going to be applying different flower seeds. And the city's using them to plant flowers all over the city. Right? And we'll just call the companies A, B, and C. And of the seeds that are bought by the company, they buy some from A, they buy some from B, and they buy some from C. Now let's say they buy 48% of the seeds from A, 32% from B, and 20% from C. They just happen to have some budget numbers that get lined up that way. Or A is kind of located in one area, B is located in another area, and that's just how it divides up, right? Now, the seeds either grow, if the seeds grow in this, we could call that G, that they grow, right? If the seeds don't grow, we'll call that G with a bar over it, like G opposite, don't grow. So for each of the seed companies, a certain proportion of the time they plant their things at intersections or different areas, and they grow, and sometimes they don't. Right? So for each of these, there's a possibility of growing or not growing. This one down. Here's enough space to get it. Oh, G, not G. Now the companies have different success rates. Company A is pretty good. 90% of the time, it grows. That 90% there would be the probability that it grows in company A. Or the probability of G, given that you're in company A, is stated at 90%. That company is pretty good. Right? Company C is not quite as good. Right? It gets 60% growing. And company B is kind of a sham. They only have 30% that grow. Spread the seeds, they don't really water them properly, they don't put straw over them or anything like that. They just dump them there and then they don't work so well. Right? So the probability of growing in B is just 30%, and the probability of growing in C is 60%. What percent of the seeds in the city grow? What's the probability of G? How would you think about figuring that out? That's one question we can ask, right? What's the chance that it grows, right? What's the chance that company A's planted it and it grows? I'll go to a new page. Right? So what's the probability that we're looking at company A seeds and we're looking at growth? So A and G, these two things together. Well, we can look at the chance of the proportion that go to A, right, and the proportion that grow in A. 48% of the time, their company A is planting those seeds, and 90% of the time they're growing. 0.432 there. But that's one company. You might have used the other companies. So what's the probability of B? We use company B and they're growing. We're going to do kind of the same thing, right? We're going to take the probability of B times the probability of growing for that company, and that'd be the fraction of the time that it's company B and growing together, both things. So this company is used 32% of the time, but only 30% of the time it's growing, so that's a smaller number. Company C and growing, and that's the third way we can get seeds that are growing. One company has to plant it. Probability of C times the probability of growing in company C. So 20% of the time, seeds gets a smaller proportion. They get 60% growth, so that's 0.12 up to the 0 term. So the chance that we get a seed planted and it grows, right, these are the three ways it can happen. It has to go through one of these companies, right? So we're going to add these things up. The chance that a random seed that we have planted grows is going to be the sum of those three things. Probability that A and growing, B and growing, A and G, plus the probability that it's company B and it grows, plus the probability that it's company C and it grows, and you add those things together, you get 8, 5, 14, carry 1, so 5, 6. About 64.8%, about 65% of the seeds that get planted work. Right? So that's about 2/3. Right? Not bad, not great. In this chart, in this tree, it's often, you can find some of these numbers, right? So if you multiply these down this way, 0.4 times 0.48 times 0.9 is 0.432. This one was 0.096, and this one was 0.120. And these are the three endpoints here where we have growing seeds. And we added up those endpoints. We had to take the chance that you go down this branch times the conditional probability to get those. What's the chance that the seeds don't grow? Yeah.
It's 100 minus the chance that they do grow.
Yep. One way to do that, which is perfectly valid, right? You either grow or don't grow. Right? Other variables you might have recorded: grow well, grow poorly, grow not at all. Right? You might have had more levels. In this one, we just have 2. So the probability you don't grow is 1 minus that, 0.352, about 35% of the time. But there's another way to do that, right? By growing, right? This calculation. All right, you can figure out the probabilities on the other parts of the tree. Right? So this is a conditional probability that it grows for A. What's the probability that it doesn't grow? 0.1. Yes, 0.1. Yes. So 90% of the time it grows in A, 10% of that company's seed fails. Right? Conditional probabilities work like other probabilities that way, that, given the denominator, given that you're in company A, it either grows or doesn't grow. And those two things add up to 0.1. B only had 30% growth, so 70% not growing. And C, 60% growth, 40% not growing. So the probability of not growing among C, to put one of these down here. Right. C is the denominator, so 1 minus. Right. 1 minus the probability of growing in C, 1 minus 0.6 is 0.4 at 40%. So the other way we can calculate the probability we don't grow is to use the table, right? Use the charts, right? We got 3 places they don't grow. That goes green, right? So here's the Here's the no-grow places. And this all is figuring out this one, the probability of don't grow this way, is something that gets referred to in this book and others. It's this law of total probability. Right? The probability of something. Now this A and B don't correspond to those companies necessarily. Right? Can be, if you get the probability of that event A with all the other different levels of another variable. In this case, B1, B2, B3. In this case, before there's the three companies. And add those up, you get the probability of that event. Right? And if we know conditional probabilities, you can do something just like we did here. Right? So, not growing, you multiply down the branches. This one's 0.048. This one's 0.4, 21, 22. That is these two numbers should add up to 32 because I've split it here. So 30, no, 20, 21, 22, is that right? What am I doing with that? Yeah, that will be that's fine. And then this one is 0.08. Keep an extra decimal place. So if you add those three things up, 0.048 plus 224 plus 0.08, it should get what we had before, so there'd be a 2, carry 1, 6, 14, 15, carry 1, and 3, right? Same number. So either 1 minus, if you've done the other calculation, or this. Any questions about that? Yeah.
I don't think I got a packet.
Oh, you didn't get the handout. Anybody else either? Sorry about that.
That's fine.
Most of it's on the board so far, but. Oh, it's okay. So now you're looking at a plot of land and the flowers grew. What's the chance that company A did it? So now we have a new scenario. We're looking at a plot of land. We have a plot of land. The flowers have grown, they look beautiful. Did company A plant it? What's the probability that company A is responsible for this, given that it's growing? That's a reversal. Before we know the success rate of this company, right? A had a pretty good success rate. Now we want to reverse it. Right? So how do we do that? Well, we could go to our definition of conditional probability. The numerator is the probability of both things. Both of these things. Which one goes on the denominator?
P of G.
P of G, right? So G is the denominator. G is what we know. So you think about it out of that. That's like in the base, like a fraction. But these two things, right? We know probability of A because we know what percent of the contracts come there, and then we know the characteristics of that company. So we can put that one there, and then have our P of G here. And so it's reversing the probabilities from what we're told to this one, along with figuring out that the law of total probability we get that one. So A was, what was A in all? Was 48% of the contracts go here. It had a 90% success rate. The chance of growing overall was 0.648. So this is a 0.432 over 0.648. And growing 0.667. So given that it's growing, about 2/3 of the time, A is responsible. In terms of contracts, A's had 50% of the, 48% of the contracts, but they're responsible for about 2/3 of the growing spots, right? So we've updated those probabilities given this combined information. Why does it go up? Why does A become more likely in the places that are growing than overall? Yeah.
Because the majority of their seeds grow.
Yeah, A does a better job, right? The other ones have less growth. So if there is growth, it increases A's chances of being responsible. Right? So if you look at this, right? So out of these 3 places that we have growth, we added those up to get the total of the 0.648, right? And what we're calculating of these 3 locations, this is the amount that is for A. So it's the 0.432 out of these 3 places together, and that's the chance of A now that we've got information that we've updated. We see that it's actually growing. What's the chance that it's A if it's not growing? So that the story for this, a plot has no flowers, is company A responsible. So we calculate the probability that A did it, given that it's not growing. So it's going to be a reversal of the probabilities like before. You can go through the steps, but the numerator is going to be reversing things. The denominator now is the chance that you don't grow. And so that was 0.352 down here. And that numerator, A was 48%, but only 10% of the time did its seeds not grow. It's a good company. So 0.048 out of 0.352, and A does not grow. I don't have that one calculated, but it looks like it's, less than 20%. Right? It's a smaller number. Right? If it's not growing, it's probably not A. So even though they have 48% of the contracts, the chance that they're responsible for a bad plot is less. So this is an example of something called Bayes' rule, or Bayes' theorem. Right? As we're using it, it's primarily a reverse conditioning by using conditional probability. Right? Thomas Bayes is a mathematician, philosopher, minister back in the 1700s, who wrote an article about reversing probabilities and updating information. Right? The modern implementation of this is a whole branch of statistics and things like personalized medicine, having your treatment based on all of your conditions, including your genetics, is what's the best for you, is estimating a probability that you should do a certain treatment path given all your information. So that's Bayes in terms of using information. And this type of calculation of updating things is kind of a very formal thing. And it's intersected with statistics and computing and the power of computers to take on enormous problems, like modeling the weather, and modeling entire history of baseball, modeling large economic systems and interactions of thousands of companies and things like that. Given that you have some new information, how does everything change? Right? So it's for ours, it's going to be of this sort, where there's a couple of steps. You could expand it to 3 steps or 4 steps, and more complex trees and things like that, where they don't have to have 2 levels in each one. Like we had 3 levels at the beginning. You can have many levels in there, and be that application. Any questions on the application of this? So new application as described in the handout, right? Breast cancer screening. So in screening things, it's important to look at what population you're talking about. Right, so these are women at age 40 who participate in regular screening. These are not women who are 80 or 60. Right? 40. So it's that population, and they participate in regular screening. 1% have breast cancer. of the women with breast cancer, if they have a mammogram, 80% have a positive mammogram. Positive meaning it detects in the group if they actually do have breast cancer. But some women without breast cancer, when they get the mammogram, also it looks positive. Right? There's something in the tissue that suggests, maybe you should check this out. So 9.6% positive mammograms, if not, if no breast cancer. How would they know that they don't have breast cancer? Well, they probably follow up, do more extensive tests and things like that. Maybe do a biopsy or something. So that's 9.6%. So a 40-year-old woman participates in routine screening and has a positive mammography. What's the chance that she actually has breast cancer? So we now see a positive mammography. What is the chance of breast cancer? So in this course, you can write things in words as you see fit, or you can use symbols. You can make up your own symbols. You don't always have to use A and B and C. You can use things like BC for breast cancer, C for cancer, and not C for no cancer.
Or you can just see with a line.
C with a line, yeah, or C for no cancer, or no cancer. But whatever is easy to keep track of things and communicate things. I think some people are fine when it gets abstract and it's all X, Y, and Z or A, B, C. But really, you can use whatever is good for communication and keeping track of the context. So what should we do to answer this type of problem? How would they know this information? Right? You can always, that's kind of interesting to know. 1% breast cancer. Right? Some parts of the country have a cancer registry. There's something called SEER, cancer registries. This is really a big thing, actually. There's, I think, 32 different registries across the country. Some states, like Georgia, every cancer that occurs in the state is supposed to be registered and reported. What's the diagnosis? What's the initial treatment? And it's supposed to have some follow-up, right? LA has one, and as part of the Centers for Disease Control, that's how they know rates of cancers and diagnosis. So with the AIDS epidemic, there were certain types of cancers that became more common that were really rare among certain groups of individuals, and suddenly, boom, here's all these cases. Like, wow, that's just unusual, right? So it's very useful for emerging things, rates over time, right? Positive mammograms if somebody has breast cancer. Well, you would have a group of individuals with breast cancer that are this 40 age, right? And so if a health insurance company or the CDC or a research company could, given that you have women have that diagnosis, they could see what rates of detection they would have. You probably want to do it so that the people didn't know they had breast cancer that were evaluating them, so it's blinded, right, or double blinded, I guess, so that the because if evaluators know you have cancer, they're probably going to say, oh yeah, that's probably cancer, right? Do it in the mammography, right? So something like that. Of individual volunteers who don't have breast cancer, right? You could evaluate them in a fair way as well. And still some percentage get that right. So mammogram, positive mammogram could be a capital M. So putting this in terms of symbols, right? The probability of cancer is 1% in this age group. The chance of a positive mammogram if they have cancer, right, is 80%. All right, 800. Probability of a positive mammogram if they don't have cancer was 0.096. On the homework that's assigned, there's some pretty small numbers, right? So it's like incidence of certain diseases. So it's like 300 per 100,000, and I give an example on the homework of converting that to a decimal. But there's a bunch of zeros to keep track of. So do that carefully. So that's what we're told. Right? What's the chance that somebody does not have cancer?
99%.
So that you can immediately, if you write down the information, you take the opposites, you get something else you'll need. What's the chance of a negative mammogram? It does not show cancer in the cancer group. 1 minus that one. So the probability, if you don't have a mammogram, a positive mammogram, it is not detective. It's 1 minus this. Just like fractions, the denominator always has to stay the same. So 1 minus 0.8 is 0.2. And the chance of the negative mammogram among people who are not having cancer is 1 minus the mammogram probability for that group. So 1 minus the 0.096, 0.904. When it comes time to do an exam and you get one of these questions, you can immediately write down some of that stuff. And then put it into a tree. That's going to be a question, right? If we're thinking about this, because it's important to be able to think about these probabilities. So what do you want to put in the first place? Yeah.
If you have cancer or not.
Yeah, the first thing you're told about you, there's a certain percentage of the cancer group or not. Right? Cancer or no cancer. 1%, 99%. And so then positive or negative mammogram test. 80% here for that conditional probability, and that 2% there, 0.096, 0.904 for those probabilities. We're looking for, we'll say, what's the probability of a positive mammogram? That's this law of total probability. That's something that we will need to compute. Take a moment and write down what you need to write down.
Is PM like the chance that your mammogram doesn't detect?
Yes, so this is about the chance of a positive mammogram test. That it does detect cancer or signals that it's worth investigating. How did somebody do this? Volunteered. Talk about, what did you do? Multiply probabilities going down the, so for this one, what did you get for this last one?
0.08.
0.008, right? You gotta move the decimal place 1. No, that's what you did there, right? And so then 0.002. It moves the decimal place 1. Oh no, I didn't do that right, did I? It's 0.0. Sorry. No, that is right. Yeah, 0.8. 0.002. So you add those two up, and we get this 0.01 back here. Right? It splits into those two points, 80% and 20%. And then if you multiply going down this one, that's 0.909,504, and this one is 0.898,496. So the chance you're positive, right? There's two places where it's positive. So we're going to add those two numbers together. So on the probability M is the probability among the cancer group of having a positive mammography result, positive test. And then you might be in the non-cancer group. They have some positive ones too. And so there's 1% here and 99% here. And this group had a 80% positive, and this group had a 9.6% positive. So that's 0.008, and this was 0.09504. So we have overall 0.10304. About 10% of the population is going to have a positive mammogram. You can always ask yourself, does that number make sense? 80% for this group, about 10% for this group. Right? So it's going to be between the rates for those two groups, but it's very, very heavily weighted toward the non-cancer group because they're 99% of the population. So it's just a little bit above their rate. Right? If you've gotten 1% or, I don't know, if you reported 1.03, you would have been missing a decimal because it can't be above 1. So you can just kind of check yourself a little bit in terms of are the numbers reasonable. So what's the probability the woman actually has cancer given that she has a positive mammogram? So the probability cancer is real given the mammogram test is positive. Well, we take the probability, reversing it, cancer, or probability of mammogram given cancer. Add those two things together. And the denominator is the probability of a mammogram. And so cancer was 1%, this is 80%, this is 10.304, so it's 0.008 over 0.10304, and that is small, 7.8%, 0.078. So even though the mammogram is positive, it's only giving an 8% chance that it's actually cancer. Is that surprisingly, are you surprised it's that low? Why doesn't it end up being 78%? Why isn't it larger? What contributes to this small number?
Only 1% of the population actually has cancer.
Yeah.
So.
1% is pretty small to start with, right? So this has jumped from 1%, just from a randomly selected woman at that age group, to almost 8%. Right? It's almost an 8-fold increase in chance. So it does make a big difference that they've had this diagnosis, but it doesn't make it 80%. It's like finding a needle in a haystack. It's hard to find evidence to really predict that tiny fraction. That's almost always true. It's hard to predict that tiny fraction. What else would contribute to it not being so overwhelmingly powerful of a test? Well, there's some chance, kind of non-trivial, that those with cancer don't get a positive test. Right? And there's a chance it's not trivial, almost 10%, that even if they don't have cancer, they get a positive test. So there's errors. It's not that specific, right? So that also means it doesn't change things quite as much. Right? What would influence this test to that probability? What would increase this probability? What would make it bigger? What makes or would make the probability of cancer given that you have a positive mammogram larger? Because if you have a positive mammogram, if that probability were larger, right, it would be more definite information. Right? If that was 90%, wow, then you're really going to, pay attention to it. Yeah.
To make it larger, I think you could get like an older population of women.
Mm-hmm. Right. So if you have, like we talked about, that 1% is a very small number. Right? If this had been 10%, as an older population or a population of smokers or people at risk, right, then things would go. Right. So how does that go through this? Well, 10% would put more probability up here in this one, so there'd be less probability down on this one, right? And so in the relative split, there'd be more probability up here than down here. So given that you had a positive mammogram, there'd be a bigger percentage in there. Let's run through that real quick. So if the probability of cancer is higher, let's say cancer versus no cancer, say it's 10%. This might be for an older population. In another application, prostate cancer among older men is actually pretty high. It's something that's usually not fatal if individuals get it at 80 or 90 years old, but it develops quite a lot, right? And it's a slow-acting cancer, and most of the times not fatal, or typically if it starts very old. Right? All these other numbers are the same. Mammogram negative, mammogram positive, and this was 80% and 20. This was 0.96 and 0.904. Then you get 0.08 up here, and that number is smaller, 0.8. This is 0.0864. So then the probability of a positive mammogram is 0.08, 0.864, 0.1664, and our probability of cancer, given that the mammogram is positive, is the 0.08 over 0.1664, or about 48%. So instead of 8%, now it's 48%. And we've gone from 10%, it's about a 5-time increase in the probability in this case. And it's making more of a difference in those numbers because this was not as rare. Right? We increased the relative proportion up here versus here. So if there's more cancer, it's more predictive. Right? There's other ways you can influence it. If we got an improved mammogram, a digital mammogram or a mammogram with new training to make it better, if this were higher and this were lower, right? If we separated the groups better. We'll talk more about that on Monday, about things called sensitivity and specificity of tests that come up in diagnostic testing all the time. And if those two things could be better, if this was 90% and that was 2%, then it would be more specific and get better probability there. But any questions about? One more question on this. Right, so this would be it. Also, probability of a positive mammogram, if that were higher, the probability of a mammogram, given that you don't have cancer, if that were lower, that would make the test better. Right? And so that's the public health, part of the public health debate is that at what age do you start recommending that women get tested? If you go to 35, 30, 25, the rates are so low that it's just not very predictive, right? And there's an expense of doing it, there's anxiety of a false positive that is probably not warranted as a general procedure. But at some point, the probabilities get high enough, 50, 60, 70, that you say, yeah, there's a definite benefit, that the probabilities get high enough that 10% of the population might have it with this procedure. So it's 50%. Maybe that's enough to recommend it. Gee, you probably should get tested because it's predictive enough. But that public health trade-off is somewhere in that range. On the other hand, let's say that the mammogram is negative. Right? What's the probability that you don't have cancer, the woman does not have cancer, given that? And this is back at the chance of the cancer is 1%. Right? We could answer that question too. The Bayes theorem. Now, you don't necessarily have to completely memorize all the formulas. You have to be able to step through them. So when you have something like this, so mammogram, this is the diagnosis. What's the chance of cancer? No cancer. No cancer. If mammogram is negative and does not detect it. Well, the M, the opposite of M stays in the denominator, so that could be something to do. And you can have the probability of both things in the numerator. So mammograms were positive. Say we just calculated it that one way, where is that? Was 0.10304. So that denominator is 0.89696. And no cancer was 99%. Mammogram negative among that group was 904. And so that part of the table was 89496. And that's pretty high, right? It's probably above 99%, I'm not quite sure. Pretty high, right? So a negative test really kind of suggests that it's truly negative. 99% were negative anyway, and this boosts it up a little bit more, right, for a negative test. So that's a good part of this. If it's negative, it's almost surely negative. Not 100%, but pretty surely. The other way doesn't tell you as much information. This information is one last thing that's in this. Sometimes they come from a table of counts. Right? So let's say we had 10,000 women. A random sample of 10,000 women. And we had two categories here, 10,000 women. And we had ones with cancer and the ones without cancer. The 0.01% would translate into about 100 women. 1% of 10,000, this is 100. The 99% would translate into 9,900 women. And some of these women would have a positive mammogram and some would not have a positive mammogram. Based on what you remember of this problem, can I fill in any more numbers? How many women would have both a cancer and a positive mammogram, according to these rates? Yeah, one.
Wait, are we going
So we have 100 women.
Yep.
Right? And so of the ones that had cancer, right, the probability of a positive mammogram among cancer was 0.8. Right. So out of those 100 women, we expect about 80. Right? We expect 80 over here, which would put 20 over there. And then out of these 9,900, the probability of mammogram if women do not have cancer was 0.096. So if you took 9,900 times 0.096, you get some number. In the table, it would be 9,504. 9,504. I know that because the decimal is 0.09504. No, that's not quite right. It's 950 approximately. So I'm off by one. Another decimal place. So if I made this out of 100,000 women, it would come out exactly even. It's about 10% of that is 990, and it's a little bit less than that, right? So 950. So that would imply that there'd be 8,000, some here, 8,950, right? Over there, so we have 8,970 positive mammogram, and 1,030 here for the 10,000 is how they would split up. So you might have data from a 2x2 table like that, right? And this gives it a 1% rate, and this gives a 99% rate. And then within that row, you get 80% and 20% and so on. If I made it 100,000, then I could use all the decimal places and it would work out. So you can kind of reconstruct tables. This is what this population looks like. Right? And these are the rare cancers, the rare positive tests that are in there. Right? So that's conditional probability, right? So you can use it for lots and lots of examples for thinking about things. often as possible, divide the population up into, men and women, or by age groups, or race ethnicity groups, and then look by rates of things happening within those groups. And a lot of government statistics on poverty, on education, on health are reported within categories, and then the population shares. And so you could reverse that, right? Once given one set of numbers, you can take it the other way or compute margins of the variable you're not told about explicitly. So we will look at other aspects of reporting additional probabilities in health and medical and biological studies on Monday. Is there anybody who did not get their homework back? Yeah, most of them.
Yeah, just some of the programs on R, or some of the commands on R, pretty much, so I just need to know.
Okay. If you can print it, or, so, yes.
Seriously,
Good, great. There you go. Yeah, thanks.
sorry, it isn't sticky.
All right.
Have a good day.
I'll come right back to that homework.
Okay.
All right, thank you so much.
I'm going to go over my office. So
Okay, well,
259, John Day 259, just down the stairs around the corner. So.
that's it, thank you.
Sure. And if it takes longer and, I'm gone, you can slip it under the door or email me a PDF if that
Okay.
goes. Either one is fine. Great. Thank you very much, Jake.